Chapter 4, Section 1. In this section, we're going to begin looking at local maxima and minima. What is a local maximum and minimum? Well, a local maximum is any point when you're at the top of a hill, and a local min is going to be any time that you're at the bottom of a cup. So any time that you hit one of these pivotal points, we have something called a local max and a local min. Looking at the graph in front of you, we can see that we're going to have a local maximum when x equals 3, because you're at the top of a hill, and also at x equals 9, because again, you're at the top of a hill. We're going to have a local minimum when x equals 6, because that's where you're at the bottom of a cup. How do we find local maxes and mins on graphs? Well, if you look at a graph, generally you can see them, and they're easy to identify. Let's start by looking at the graph of y equals x squared. You can see that we're going to have a local minimum at x equals 0, because that's where we're at the bottom of a cup. So let's look at the math behind this and see if we can figure out from the graph how the math would relate to it. Well, to the left of x equals 0, we see that the graph is decreasing. That means that the derivative is negative there. To the right of 0, we see that the graph is increasing, so we know that the derivative there would be positive. If you look right at x equals 0, and you were to draw on a tangent line right at x equals 0, it would be a horizontal tangent line. That's going to be key to finding our local maxes and mins. So let's look at this in chart form. To the left of x equals 0, we said that f was decreasing, so the derivative was negative. We said to the right it was increasing, so the derivative is positive. And we said right at x equals 0, our derivative is 0 because we have that horizontal tangent line. So any time that we have that the first derivative equals 0, we call this a critical point. This is going to be important because in order to find local maxes and mins, the first step is going to be to find all of these critical points. Once we've found them, there's different ways to classify whether or not this point is a local max, a local min, or neither. So how do we find these critical points? Well, like we said, we want to know when the first derivative equals 0. So let's say we have a function 3x squared minus 6x plus 4. To find the critical points, we want to take the first derivative and set it equal to 0. So our first derivative is going to be 6x minus 6. We set that equal to 0 and we solve for x. So we get 6x equals 6, so x equals 1. This is the critical point. Our critical point is at x equals 1. If you're asked for a critical value, that means they want the y value. So you would take that critical point and plug it back into the original to get the y value. So if you were to plug x equals 1 into the original function, you'll get y equals 1 as your critical value. Let's look at another one. Let's say f of x equals 2x cubed minus 3x squared minus 12x plus 4. Again, to find the critical points, we want to take the first derivative and set it equal to 0. So the first derivative here would be 6x squared minus 6x minus 12. We set that equal to 0. Usually when you have a polynomial with a degree of 2 or higher, you're going to want to factor it. If you're not comfortable with factoring, go ahead and use a quadratic equation, but if you like to factor, go ahead and do that. So once you factor out the 6, you're left with x squared minus x minus 2, and that can be further factored into 6 times x minus 2 times x plus 1. And again, we want to know when that equals 0. So this would be 0 when x is 2 or when x is negative 1. So our critical points will be x equals 2, from the first parenthesis being 0, and the critical y value will be negative 16 from plugging that 2 back into the original function. And the second one will be x equals negative 1 with a critical value of y equals 11. So like I said before, finding the critical points is going to be the first step, because every time you have a local max or min, you're going to have a critical point. So now we need to figure out how we classify those critical points to figure out, are these indeed maxes or mins or neither? So we have two different tests that we can use to classify them. The first derivative test is going to look at either the original function or the derivative, and it says that if f changes from increasing to decreasing at a point, then f prime of x changes from positive to negative at that point, which makes that point a local max. So what we're saying is if you're increasing on the left and then decreasing on the right, you're making a hill, so that makes it a local max. Similarly, if f changes from decreasing to increasing, then the derivative changes from negative to positive, which makes that point a local minimum. Now, these rules seem a little bizarre, but when you put them into practice, they work really well. However, I recommend writing them down or printing out this screen so that you have these rules in front of you, because it's very easy to confuse the rules. The second derivative test uses the second derivative to figure out if we have a local max or min. If f is concave up at a critical point, then that means that the second derivative is greater than 0, because remember, the second derivative tells us about concavity. So if you look at the picture of concave up, you can see that if it's concave up, that point is going to be a local minimum. Similarly, if f is concave down at a critical point, then the second derivative is going to be less than 0, so that point will be a local max. Now, you can use either test, you don't need to use both, so you can pick the one that you're more comfortable with unless it's explicitly stated that you should use one or the other. Let's look at how we would use the first derivative test. So let's say we have the function 2x cubed minus 3x squared minus 12x plus 4. This is the one we looked at before. We found our critical points to be x equals 2 and x equals negative 1. Once you have your critical points, you need to classify each one separately, so you look at them one at a time. So let's start with x equals 2. We need to look at what's happening on the left and the right. So what does that mean? That means you want to pick a number to the left of your critical point and to the right of your critical point, and what we're going to do is we're going to test them with the first derivative to see their signs. So if you take x equals 2 and you look a little to the left, a good point to pick would be 1. So if you take the number 1 and you plug it into the derivative, you're going to get the value of negative 12. So again, you're plugging that into f prime of x because you're using the first derivative test. We also need to look to the right of our x equals 2 because we're looking at if the sign changes. So here, something a little to the right of 2 would be the number 3. So if you take 3 and you plug it into the first derivative, you get the number 24. Again, it's not the numbers that really matter, it's the sign that we're looking at. If the first derivative goes from negative to positive, that means the original graph goes from decreasing to increasing, which makes x equal 2 a local minimum. So now we want to look at our second critical point and do the same method. So our second critical point is x equals negative 1. If we pick a point a little to the left of negative 1, we can pick the point x equals negative 2. Be careful with negatives. If you move to the left, it becomes more negative. So here, when you take negative 2 and you plug it into the derivative, you're going to get 36. Now we want to pick a point that's to the right of negative 1. So again, be careful with negatives. We can pick the point 0 because on a number line that would be to the right. So if you take 0 and plug it into your derivative, you're going to get the value of negative 12. So that means here, from left to right, we're going from positive to negative. That means the original graph is going from increasing to decreasing, which makes x equal negative 1 a local maximum. Now let's look at how we would do the same example using the second derivative test. Again, I remind you, you don't have to do both tests. You can use whichever one you like. Most people find the second derivative test to be a little easier. However, you do need to understand how the first derivative test works because sometimes there are questions that require you to use it. So again, keeping the same example, we know that the first derivative of our function is 6x squared minus 6x minus 12, and we found our critical points to be x equals 2 and x equals negative 1. To use the second derivative test, we need to calculate the second derivative. So again, the second derivative is the derivative of the first derivative. So our first derivative was 6x squared minus 6x minus 12. So the derivative of that is going to be 12x minus 6. So once you have the second derivative, you are just going to plug each of your critical points in. So we take the second derivative and we plug in 2. That was our first critical point. So you get 12 times 2 minus 6, which gives you 18. If the second derivative is positive, as 18 is, that means it is concave up. If it's concave up, it looks like a cup, and that means that critical point is a local minimum. We also want to test the second point, so we're going to plug in negative 1 into our second derivative, so we have 12 times negative 1 minus 6, which will give you negative 18. Again, the number is not what matters when using the first and second derivative test. We're looking at the sign. So here it's negative. If the second derivative is negative, that means the original graph is concave down, which looks like a hill, which makes this a local maximum. So again, you can see that we got the same conclusion as using the first derivative test. Both will give you the same conclusion, but use whichever one you're more comfortable with. One word of warning: not every critical point is a local maximum or minimum. If you do the first derivative test and the sign does not change, so that means if you look a little to the left and a little to the right and they're both positive or they're both negative, or if you do the second derivative test and it equals 0, so that doesn't have a sign, then you have neither a local max nor a local min. So let's just do a quick example of that. If f of x equals x to the 5th, then our first derivative is going to be 5x to the 4th. To find our critical points, we set that equal to 0. Well, 5x to the 4th will be 0 when x equals 0. So x equals 0 is our only critical point. Using the first derivative test, we want to look a little to the left, so we can plug in a negative 1 into our first derivative. Negative 1 to the 4th is positive 1 times 5 is 5. And then we also want to look a little to the right. A little to the right of 0 is positive 1, which you plug it in 1 to the first derivative and you get 5, so there's no sign change. If the derivative doesn't change sign, that means you have neither. Similarly, if we were to do the second derivative test, again, you would take the derivative of the first derivative to give you 20x cubed. Plugging in the critical point of 0 gives you 0, so there's no sign. So if either of these cases occur, then your answer would be neither. So go ahead now and try to do some of the homework from Chapter 4, Section 1.